Okay, the first speaker needs no introduction. Is our chairman, who is going to talk about coherent states attached to Landau levels on two-dimensional surfaces. Okay.
Thank you, Chairman, Professor Burdas. I would like to thank you for being here and for this opportunity to talk about this subject. So coherent state attached to Landau levels on two-dimensional surfaces. So what a coherent state means, it was Schrödinger Nobel Prize, 1933, who was the first to introduce this notion for the harmonic oscillator, that are states that minimize the Heisenberg uncertainty. And the closest expression of this coherent state are given by Formula 1 in terms of this exponential. Indeed, these functions minimize the uncertainty, and his is the fluctuation with respect to any state in L to R. So the harmonic oscillator decomposes in A star A, annihilation creation operator, and there is the definition of Glauber, 1951, eigenfunction of the annihilation part of the harmonic oscillator. It simply means that there are states that do not feel subtracting photons. So you act on this state and you do nothing. It's just multiplication with the complex number Z. And this is a classical feature of these states. In physics notation, they are written in terms of the ket with the Z, Z notation. So he is Glauber, a Nobel Prize in 2005, and he is he's writing in the blackboard a formula, another formula of this coherent state, and this formula is in fact the expansion of this coherent state in terms of the basis, orthonormal basis of the eigenfunction of the total Hamiltonian, the harmonic oscillator. In blue, this is the formula Glauber was writing, and it is usual. Sometimes we call it the ala Iwata, as Professor Dodonov here wrote in his survey, 17.5 years of squeezing the coherent state. And in physics notation, we write instead of the function just the index n. And alpha, as you see in the blackboard there, alpha is the Z notation. So this is just to put notation physics and mathematics. And if we take the square root of these coefficients, this gives the Poisson distribution. So we have a probability there. So for summary for the harmonic oscillator, coherent state can be obtained by 4 ways. Expansion, minimizing uncertainty, and displacement operator, and I mean, we have all the way to perform coherent state for the harmonic oscillator, 4 ways. And they solve the resolution of the identity. I am explaining what the meaning of this Dirac bracket notation is. The rank 1 operator, scalarize and then project. And it forms an overcomplete set, and they are not orthogonal states in L to R. So, why these coherent sets are important? I will give us an example. It's appeared in Science Review. It's like satellite testing of gravitational induced quantum decoherence model. And as you see, between the satellite and the receiver on the Earth, we see here a device, and inside this device, you can see that we have a coherent state, meaning that the coherent states are macroscopic in some sense, and we can construct them in laboratory. And this is in technology for the future, for security of information, for a lot of things. So coherent states are not just mathematical or theoretical physics objects, but they can be constructed and built in laboratory. So now, in the next slide, I will talk about the generalization of the number state expansion, what we call probabilistic Hilbertian scheme, talk about some integral transforms attached to this coherent state. I will talk about quantization, dequantization via a set of coherent states. I will talk about some probability distribution attached to this coherent state. So probabilistic Hilbertian scheme. What is the meaning? Now, we are taking coefficients and labeled by point on the variable are the phase space, an orthonormal basis on a Hilbert space that will be the quantum Hilbert space of the phenomenon or the Hamiltonian we are working with, the H, and with the normalization condition, so the X for which this is finite, we can define this coherent state. Now, this is the formula. This formula is a generalization of the number states expansion of coherent state. You need two bases, practically two bases. One of them, I will call it phi k, is physics. The other one, ckx, is more mathematical. I mean, basis of some functional space. So, ck are orthonormal bases on some space in L2x. X is a phase space, generally with some measure. And we will face the problem of the resolution of the identity. And this problem will amounts to solve some moment problem. This is not an easy task. So you can combine two bases, but you should, we should answer the problem of the resolution of the identity. Now, there are many definitions, but they are Cloder tree condition. Continuity with respect to the label, resolution of the identity, and normalization, so that's the minimum condition. And then once you have done this, you can take the square modulus of the projection on a phi k or a number state, and then you perform a probability distribution. And you will see that probability distribution there, this probability side is very important in the second. So integral transforms. So once you have a coherent state, you have automatically, I mean, in this concept, in this Hilbertian scheme, we have an integral transform. You have to put a scalar product with a function in the Hilbert space H. So I will give example. It's better than I give example than talk too much in the theory. Harmonic oscillator, isotonic oscillator, Krautchuk oscillator. So let us see for the harmonic oscillator I just talked about. We have the Hamiltonian, we have the Hilbert space L2R, we have eigenfunction, Gaussian Hermite functions, we have the coefficients that are analytic basis of the Fock-Bargmann space, analytic Gaussian square integrable, and I have added some aspect of group aspect because they are displacement, because they are representation there. Schrödinger representation there, we can recover them by a representation theory of square integrable representation. Sometimes directly on the group, sometimes square integrable modulo the quotient and some Borel section, etc. Anyway, now when we perform the coherent state transform, what we found? We found the Bargmann transform. This is the Bargmann transform. Now, what is the meaning of the Bargmann transform? It is the coherent set of the harmonic oscillator. What is the harmonic oscillator? Is the potential, x squared. So another example is in the hyperbolic geometry. Motion space, it should be the half line, the positive half line. Phase space is the Poincaré upper half plane or the disk. The geometry are conform there, the disk, the upper half plane, the pseudosphere, something like that. The Hilbert space is L2R plus. Eigenfunctions are given by the Laguerre functions. The coefficients, the mathematical coefficients are given by these analytic functions. And the space is the Bergman space with this weight, the weighted Bergman space on the disk. The group behind the symmetry or the representation theory or the Gilmore-Perelevov construction is SU11 or the Affine group, one of these representation, and we can play with the Cayley transform and write different kind of indexation. Anyway, the Bargmann transform here is given by this expression, and it is called the second Bargmann transform. It's appeared in the same paper of Valentin Bargmann, 1961. The next one, the phase space are points, a finite number of points, and the X is the Riemann sphere, or the complex projective one, or the Alexandrov compactification of the plane. The Hamiltonian is the Krautchuk oscillator. The Hilbert space L functions that are square integrable or summable on this finite number of points. The coefficients are given by these monomials, and here we have also a kind of Bergman. It's like a duality between the spherical geometry and the hyperbolic geometry. This is a question of sign plus or minus. The group SU2, we can write it parallel of construction with some representation given by these two authors. And here is the Bergman transform. People don't call it Bergman transform, but this is the Bergman transform in this setting. So, we call it the third Bergman, if you like, third Bergman transform. So, observation from previous example. Previous example of the complex plane, the unit disk or the complex projective are these analytic coefficients. And these coefficients constitute some orthonormal basis in some subspace of L2X. And this space A2, in this example, turned out to be the eigenspace of the Hamiltonian of uniform magnetic field, normal to the phase space, associated with the lowest eigenvalue or the lowest Landau level. So, what is now the idea? These coefficients are encoded, in fact, by the magnetic field, the Hamiltonian of the magnetic in these three models. And now the task is to extend this construction to higher Landau levels. Now the magnetic field is there, but the magnetic field normal to these surfaces. So. Why Landau levels are so important? Because they are associated with the classical Hall effects. So you know the classical Hall effect, magnetic field, normal, and then we have some current there. And these many scientists, mathematical physics, physicists, and there are, sorts of Nobel Prizes about this problem of Landau levels. And the recent one is the quantum geometry, and is 2016 about the integer quantum Hall effect. So Landau levels are associated to the Hall effect, and the Hall effect is very important in technology. And now, what we have done as a Moroccan team since 1997. We were considering this Laplacian or this operator, which is in fact an intertwining form of the Hamiltonian magnetic field, and written in a complex variable. And then we considered these eigenspaces associated with this operator, which turned out to be eigenspace of the Hamiltonian for Landau level M. And for 0, m equals 0, we recover the Bergman-Fock space. And this space, mathematically speaking, is the space of M true polyanalytic functions. I mean, you know polyanalytic function, but you have to do this orthogonal difference between two levels. And we can call it eigenspace of the Landau operator in a complex variable, or you can call it the M true polyanalytic space of M true polyanalytic functions. So, first result is that if we replace the coefficient, the analytic coefficients by the polyanalytic coefficients, we construct coherent states in the Hilbertian probabilistic scheme. We can build this integral transform. And this, we can call it the Bergman transform of index M, of index Landau level M. For M equals 0, it's the Bergman transform. So, now, we can move to the Poincaré upper half-plane onto the disk, and we do the same game and look for eigenfunctions for this Landau level in the hyperbolic case, and get the basis there, put the coefficient there, and construct the coherent state, and then get this integral transform. Of course, this integral transform of index M is generalizing the second Bergman transform. So this is also a work with the Moroccan team. with Professor Wassouli here and a colleague from Rabat, and Professor Ntisar passed away. And we're still working on this kind of questions. And the last one, the spherical geometry and Riemann sphere, the same game. We look to the magnetic field there, and then look for eigenspaces and look for these energy levels and choose one of them and put them in the Hilbertian probability scheme, and then construct the coherent state and the integral transform. Here, the integral transform is a summation. We are in discrete case, and we can generalize this result of these two Iranian colleagues. This is idea about integral transforms we can build from this coherent state. Okay, so now we have added more complication. We have now the beta deformation of this M polyanalytic coherent state, and we have the Q deformation based on Q calculus. So for the beta deformation, we start with another game. Instead of facing the moment problem, we start with the measure and we construct the moment. And we have to replace the polyanalytic coefficient by another two-dimensional complex polynomials. And this work have been done with the Khalid and with the Touareg, Sid Ali Touareg, who passed away. And Khalid Habli will talk about this in more details in his talk. And just to remember this scientist, a very great scientist, I am working with him in Concordia University in Montreal, and the idea was interesting, not to face the moment problem and the resolution of the answer, but start with the measure, and then you get the moment, and then you get the generalized factorial in the denominator of the analytic coefficients. So he passed away in 2016, and this to have some thought about him. And now the Q deformation of this polyanalytic coherent state or transform, there is some result with Uthman, and he will talk about this in his speech. And once you have also coherent state, you have idea about the range of the integral transform. The space with the range is the reproducing kernel can be obtained just by the overlap of the coherent set. When you overlap of two coherent sets, you get the reproducing kernel of the arrival space of the integral transform. So this result are published in 2018 with Sama and with Al-Mu'izz, and he will talk about this in more detail. I mean, we have a lot of programs. We can deform this polyanalytic in many ways, Q or beta or something like that. Now, summary. Specific choice of Schrödinger, one-dimensional Schrödinger operator, I mean potential, coherent state integral transform. And one question, do known mathematical transforms originate from specific choice of one-dimensional operator, one-dimensional Schrödinger operator? You see, the story is that when you fix the potential, you have the Hamiltonian, you consider this thing, and you end up with some integral transform. And we have in mathematical literature a lot of integral transform, and the question, I mean a naive question, could this integral transform we know, even Fourier transform or other, originate from a choice of some potential? This is a question. So they are useful because they can make a bridge between the quantum state space or signal space state and the representation by analytic function and the stellar representation and so on. And frame quantum signal side, sampling on the analytic side and other things. Maybe Daniel Abreu, who is here, will talk more about this signal side and this kind of things. Okay, so now quantization, dequantization. So what is a quantization? Look, we have a resolution of the identity. We can see this operator as a quantization of the function 1 over the phase space 1, the function 1. It's every complex number z, you put 1, and you put it in the weight there, in the measure. And now, you take an observable, classical observable, a function on the phase space, and then you can construct this operator. Quantum observable. Example, if you take the quantum observable ZZ bar, which is the energy, PQ squared, Q squared, then you get the harmonic oscillator by quantization by the classical coherent state. So we have a way to transform classical observable to quantum observable via a set of coherent state. We have this possibility. So when you choose the classical observable as the indicator function, you end up with this story of localization operator in signal analysis, because signal analysis or quantum, they are similar in many ways. And here is one of the good reference for that is Ingrid Dobici's paper. And I mean, when you choose this indicator function, you are in the story of localization, and there is many things to do there from mathematical viewpoint. And we want to investigate spectral properties of the quantum observable on this side. I mean, the idea is not only to quantize, but to start to study spectral properties of the results. And from the spectral properties of the result, you can get some information about the physics. So there is some recent work with Daniel and Felix on this kind of a game. We are not working with the indicator of a function, but indicator of some kind of contour. Some fractal things, object inside the disk. So now, when you dequantize, like you take an operator and then you put it in some expectation with respect to the coherent state, you are back to classical observable. So here is a way to dequantize. There are many ways in dequantize. Physicists know that, but this is a kind of dequantizing a quantum observable. Okay, so one of the things you get if you take the mixed state, you get some what we call Husimi Q function. So we have a way to quantize and dequantize. Okay? So when you quantize, you dequantize, you have you don't end up with the function you start with. You start with the classical observer, you go down and you're back, and you are not there. So the default or the difference is measured by the called Berezin transform. So this is the Berezin transform. I mean, the meaning of the Berezin transform. I don't, like to say, Berezin transform is some integral transform with some kernel or some reproducing kernel. You can say coherent state, quantize, dequantize, and then you associate to the function you start with the result. This is the Berezin transform. It is very useful, for Henkel operators, H equation, and other analysis. And the formula expressing the Berezin transform in terms of the Laplace-Beltrami of the phase space is very useful in the correspondence principle and some Simons-Zig diamagnetism inequalities. This formula is important. So we have done some calculation to extend all the result for the lowest Landau level in these three kind of geometries. This is the idea. So let us play the game. Even in Cn, higher dimension, I was able to write the Berezin coming from the polyanalytic coherent state, as I was talking about, and then able to write it with the why the Laplace-Beltrami? Because it is the free particle. Free particle. I mean, we want to express something deformed as a function with something not deformed. Now, this is the meaning of the... Of course, for m equals 0, we recover the known expression of the Berezin transform in this case. Here, maybe we need to put Cn. Now, another result is in the hyperbolic setting, in the Bergman ball. We were able also to write this kind of formula in the level, Landau level m. expressed in Berezin in terms of this operator, Laplace-Beltrami operator of the ball in Cn, and the last one is expressing the Berezin transform with the polyanalytic coherent state in terms of the Fabini study Laplacian on the complex projective space in higher dimension, n dimension. When we have n1 and m0, we recover the Berezin formula written in his paper, Communication Mathematical Physics, 1975. So, this just to give you idea about this. Now, the next point is, as I mentioned, when you have the overlap between two coherent states, you have reproducing kernel of the range of these integral transforms, and then you know that when you have this reproducing kernel, you can play the game of determinantal point process, kind of determinantal point process based on this reproducing kernel. So, and you have this story of random matrix, orthogonal polynomial, and Gaussian analytic function, etc. Once you have a reproducing kernel, I mean, now if you have coherent state, you will also go in the direction of the DPP, and one of these problem in this DPP is that the function counted the number of particles inside some domain of radius R of some ball of some domain. Then they calculate the variance and the expectation, and they see if there is some asymptotic behavior, and when the ball expands to the whole space. And so this is what we call hyperuniformity. Hyperuniformity. So it is important on those people working. So hyperuniformity is now a question of a new state of matter, because the hyperuniformity concept, I mean, is help to classify crystals, quasi-periodic systems, special disordered system, mathematical matrix full of random numbers, large scale structure of the universe, and also, I mean, scientists have found on the eyes of chicken and of birds that's, I mean, something neither regular nor random. And this is the idea of hyperuniformity. And this hyperuniformity is measured by this, this ratio, variance, expectation, this ratio. So, this ratio. So, now, let us give an example. I stay in the polyanalytic story. Let us take the reproducing kernel of the Landau Hamiltonian in C, and we have the first intensity, and the expected number of particles can be computed with the diagonal of a reproducing kernel. It's R squared, and the variance is given by this expression, and we have the behavior of this variance as the ball or the disk the radius go to infinity, and this result is written in the paper of Shirai. So what I'm going to do is, I don't want to talk about reproducing kernel. I don't want to talk about this mathematical formula. Because when you want to calculate this expectation in the variance, you have to deal with the reproducing kernel. I don't want to talk about this thing. I will say one thing. I will not work on the analytic space or the analytic side. I will just put myself on the quantum Hilbert space, L2R. I will construct coherent state. I already talked about this in the first result about integral transform. Here I have the closed form of the polyanalytic coherent state. And now what I'm doing, I will quantize. I will quantize a classical observable, and I will write the formula. And take the quantized form, this discrete spectral resolution, so that I have eigenvalues. And now, when this classical observable is radial, I get more things become simple. Because I am integrated with respect to the angular things, and then things become simple. And then we have some nice discrete spectral resolution. And then we see that this operator is sharing the same eigenfunctions of as the harmonic oscillator. Okay. And now, if people want to work on the analytic side, like Daniel, who is here, you just have to perform. You have just to perform the coherent state transfer, the embargement, and then you go there. So you can do that. Yeah, no problem. Okay, if you want to work on the analytic side, you have the Bargman transform or the generalized form of Bargman transform. So no problem. But now I don't want to talk about the analytic side. I'm just working from L to R. And I'm taking the classical observable, the indicator. And then I'm computing eigenvalues. Okay, when I compute eigenvalues, then I compute the expectation. And I know that the random variable has the same distribution of independent Bernoulli random variable. So that I compute the summation of the beta, and I get R square. I don't talk about reproducing kernel. I'm not talking about anything. Just directly, I get R square. Okay, so I'm pushing this thing in at a certain limit. Here, the things are more or less simple. Let us see for the variance. For the variance, I'm taking this classical observable. This classical observable, and then I'm doing the same game. I'm quantizing and looking for eigenvalues. And then we compute these eigenvalues explicitly. You see? So we compute these eigenvalues. And then what we notice is that the variance is, in fact, this is the key, is the Bayesian transform of this classical observable. This function, consider it as a classical observable at a point at the origin. And then I put everything in the formula of the expectation of the Bayesian transform, and then we get that our variance is a special case of these eigenvalues. So I put M equal K in the above formula, and here is, in the last formula, we have the variance. I didn't use any formula about reproducing kernel. I'm just doing, but this function, if we look to this function, it's in fact at some additive constant. It is the autoconvolution of the indicator function. So you may see, for the expectation, I have the indicator function. For the variance, I'm dealing with the autoconvolution of the indicator function. And I'm quantizing this, dequantizing, and I get in the variance. You see? So, when m equals 0, this formula of two hypergeometric functions reduce to this one, and this one by another formula reduce to this one, and this one is exactly the formula given by Ozada and Shirai. So the computations are correct. So what is the meaning of that? Summary. We recover the expectation variance with respect to the Geneva polyanalytic process of index M by quantizing the phase space with respect to the set of coherent states of the harmonic oscillator on L to R. And the spectrum of the quantum observable representing the indicator divider allows us to compute the expectation. The variance is obtained as a spatial eigenvalue of the quantum observable involving the autoconvolution of the indicator function. You see? The Bayesian transform, in fact, at the point 0. The idea we are working on, we seek to identify classical observable on C whose quantum counterparts may encode the first cumulant of the number point particle inside the disk through spectral properties. That is the idea. Take classical. We have to localize or to know, to identify whose classical observable encodes this cumulant of this. And we are talking about reproducing kernel. We are not talking about any formula about analytic side. We're just working on L to R, on the phase space. We do physics. Try to do physics. That is. And we get this mathematical result. Okay? So, in fact, my talk is on the other direction of the conference. Because I start with physics, and then I have result in mathematics. So we should say physics methods in mathematics. I mean the opposite of the title of the conference. completely. Because in physics there we have, should I have some times, Voerdas? How much?
A couple of minutes.
Yes, okay. Observation. But this is something Daniel will not like. The Ginebra type process is hyper-uniform. It was in his paper with the Torquato and the company. Okay. I mean, for m equals 0, it is hyper-uniform. For m greater than 0, it is hyper-uniform. So the DPP way through hyper-uniformity does not allow to distinguish between the lowest Landau level and what's happening in the higher Landau level. Because it's hyper-uniform in two cases. Okay. So now I will talk about another things that can make the difference, that we can see the difference between these two stories. So we have discrete probabilities coming from photocontinuous probability distribution, and this is useful in quantum optics. And we have the continuous one by Bayesian duality, and we have Husimi function, we have violent entropy, and thermodynamics. I will give an example. Better that I explain what I want to say with examples than theory. So I will take the example of the disk. The space X from the Hilbertian probability scheme is the disk. The measure is there. Everything is there. I take the Landau operator in the hyperbolic geometry. The magnetic field in the hyperbolic geometry. Okay? And then I write the Landau levels. They are a finite number, and not as the Euclidean place. They are a finite number controlled by the strength of the magnetic field. Okay, they are finite. Okay, with infinite multiplicities. To each eigenvalue, I have Bund states, and then I take the basis of any or each of these eigenspaces. I take a basis, an orthonormal basis there, and then, as you see, for m equals 0, we recover the analytic case, and then I run the machinery of writing this. This is I implemented a curvature parameter in order to, by geometric contraction, I recover what's happening in the flat case. Anyway, I construct coherent state in this way. Okay, I have no coefficients. Everything is okay. The normalization, okay. These coherent sets are generalized as the negative binomial distributions. For m equals 0, we get the negative binomial distribution. And now, the probability of having G photons in this coherent state are given by the square modulus of the coefficients, taking into account the normalization. And then I have this probability distribution. This is the photon counting of the source, not of the receiver. There are two photon counting, the source and the receiver. They are related by what we call the Bernoulli transformation. But I don't talk about the photon count of the receiver, of the source. Okay? So this is what attached to a Landau level in the hyperbolic case. And then we wrote some results with Nizar Demni, who is working in France. As a Tunisian colleague, and we have this atomic decomposition of this distribution, but we don't need it now. And we compute the generating function, and from the generating function, we extract this first cumulant, expectation and variance. You see? So, for people in quantum optics, they are interested by the Mendel parameter. Variance over the expectation minus 1. Okay. So, when it is negative, we have some sub-Poissonian. When it is positive, we have some super Poissonian. And to each kind of Poissonianity, if allowed to say Poissonianity, there is some physics behind. If it is sub-Poissonian, this is anti-benching. I mean, photons are coming more spaced. When it is positive, there is some benching. Photons are emitted in a grouped way. So you know this. So in our case, we do computation. We compute the Mendel parameter, and then by computing this, we seek where this is 0, and then we have some radius. I will skip these details. So the result. We have now inside the hyperbolic disk another disk with a certain radius, you see, with a certain radius, and when it exhibits anti-benching, which was not observed in the lowest Landau level. No anti-benching in the first Landau level. But now we have this phenomenon of anti-benching occurring at these higher Landau levels, okay? So, in this picture, the first one is an anti-benched, and the red is Poissonian, and the benching is like determinantal process when they are compared this thing to the Poisson process as a reference to say hyperuniformity or other thing. So, I will skip this infinite Levi-Kinchin representation, quasi-infinite divisibility of this probability distribution. We do a lot of things here, and we have Levi-Kinchin representation, but not true, because the measure there is not Levi, is not positive, is a signed measure, and then we cannot call it infinite divisibility. Infinite divisibility, we don't have infinite divisibility for higher Landau levels. We don't have it. We have it for the first Landau levels. But we call it quasi-infinite divisibility. Quasi-infinite divisibility is connected to the Riemann hypothesis. There is a work of Nakamura about this. I can show you these things if you are interested. So, summary. We construct CS by using orthonormal basis of general Bergman space. We performed the analysis of probability distribution arising from the CS. These general negative binomial are, for a given hyperbolic, is not infinitely divisible, unless for the analytic case. We noticed that the failure of infinite divisibility property for this distribution goes in parallel with the appearance of anti-benching region for the Kuntine statistics. Thanks.